Picture launching a spacecraft 45 years ago and having it still operate today, venturing into territories it was never originally designed to explore. Functioning far beyond its intended lifespan, that's the astonishing reality of NASA's Voyager 1, the most distant human-made object in existence. This daring mission, launched in 1977, has transformed the field of space exploration, stretching the limits of technological resilience and human ambition. What's even more remarkable is that this spacecraft, now billions of miles from Earth, continues to transmit scientific data using technology that predates the era of cassette players. And yet, despite its antiquated systems, Voyager 1 recently made a discovery that has riveted scientists across the globe, upending long-standing theories and igniting worldwide curiosity. So what exactly did Voyager 1 uncover in this remote frontier of space? And what implications might it hold for life on Earth? To answer that, we must revisit a landmark chapter in the annals of space history, when NASA launched two of its most legendary missions, thanks to the brilliant vision of Gary Flandreau at NASA's Jet Propulsion Laboratory. Using nothing more than a pencil and traditional engineering methods, Flandreau calculated a precise and efficient trajectory that would enable a probe to visit the solar system's four gas giants: Jupiter, Saturn, Uranus, and Neptune. In the late 1970s and early 1980s, a rare planetary alignment offered an extraordinary opportunity. The four gas giants would line up in a unique cosmic formation, essentially forming a gravitational pathway from Earth to the outer solar system. This rare configuration, which happens only once every 176 years, allowed spacecraft to gain velocity by using gravitational assists, slingshot maneuvers where a probe loops around a planet and harnesses some of its orbital energy to accelerate. This technique shortened the journey to Neptune from 30 years to just 12. Recognizing the fleeting nature of this celestial window, NASA acted quickly. In the summer of 1977, the agency launched two nearly identical spacecraft, Voyager 1 and Voyager 2, just 15 days apart to capitalize on the rare alignment. No one at the time could have predicted that these twin probes would go on to break every record in space mission history. Over 45 years later, Voyager 1 and Voyager 2 remain operational, continually sending back priceless data from the outer reaches of our solar system. They are now the farthest traveled human-built objects ever launched, journeying well beyond what their creators envisioned. Originally slated for a 4-year mission, these robotic explorers have proven to be true pioneers of interstellar space. From the outset, they delivered extraordinary revelations. Voyager gave us our first close-up look at Jupiter and Saturn's moons, worlds brimming with unexpected activity. Who could have foreseen volcanic eruptions on Jupiter's moon Io, or the intricate icy terrain of Saturn's moon Enceladus? These findings shattered old assumptions and suggested that even remote, frozen moons could possess dynamic geology and potentially environments capable of supporting life. Voyager 2 went on to become the first, and still only, spacecraft to visit Uranus, 1986, and Neptune, 1989, unveiling entirely new insights about regions that had never before been explored. Now more than 14 billion kilometers, over 8.7 billion miles from Earth, these car-sized probes have repeatedly defied expectations, pushing the boundaries of what we thought possible. Their innovative path began even before launch, with gravity assist techniques that had never been attempted. One early maneuver involved a precision flyby of Venus en route to Mercury, a pioneering feat that allowed the spacecraft to build momentum for the long trek to Jupiter, a trip spanning 10 times the Earth-Mercury distance and requiring navigation through the dangerous asteroid belt, a challenge only previously overcome by Pioneer 10 and 11. Despite these obstacles, the Voyager probes pressed on, powered by onboard computers containing a mere 69 kilobytes of memory, a tiny fraction of the storage on even the simplest modern smartphone. These primitive computers had to autonomously handle complex tasks like navigation, data processing, and long-distance communication. Scientific measurements were recorded on 8-track tape recorders and then transmitted back to Earth using a 23-watt radio, about as powerful as a household light bulb. Each spacecraft was equipped with a 12-foot-wide high-gain antenna that allowed it to send and receive radio signals across the vastness of space. But communication grew more difficult with each passing day, as the spacecraft drifted farther away, each day adding another 3 to 4 light seconds of signal delay. Eventually, signals from Voyager 2 took over 18 hours to reach Earth. On top of that background noise from Earth-based sources like radios, TVs, and cell phones made it increasingly challenging to detect the faint signals from the spacecraft. Still, the Voyagers delivered extraordinary results. As they approached the outer edge of the solar system, they revealed insights about regions previously thought to be empty. One such region is the Oort cloud, a theoretical sphere of icy bodies held in place by the Sun's gravity, extending halfway to the nearest star. Though the probes haven't yet entered the Oort cloud, they did achieve another milestone, crossing the heliopause, the outer boundary of the heliosphere, where the Sun's solar wind meets interstellar space. Initially, scientists believed the heliopause lay roughly 50 astronomical units, AU, from Earth. As Voyager 1 approached this boundary, NASA extended the mission. Scientists expected to detect a spike in cosmic rays, high-energy particles from distant stellar events like supernovae, as well as a noticeable shift in magnetic fields due to the influence of nearby stars. Surprisingly, though, Voyager 1 detected no such dramatic change in magnetic direction. On August 25, 2012, Voyager 1 officially entered interstellar space. The spacecraft measured a significant rise in plasma density, a telltale sign of its new environment, but found that the magnetic field's orientation remained largely unchanged. This unexpected finding challenged prevailing models and suggested that the boundary between the Sun's influence and interstellar space may not be as sharply defined as previously thought. Instead, the heliopause might be a more turbulent, intermixed region where solar winds and interstellar materials blend. Voyager 2 crossed into interstellar space in November 2018. Unlike its twin, Voyager 2 retained additional functioning scientific instruments providing even more comprehensive data. As both probes ventured onward, they measured plasma waves, cosmic rays, and magnetic fields, painting an increasingly nuanced picture of the interstellar medium. One of Voyager 2's most intriguing discoveries was the detection of subtle ripples in the plasma, waves likely triggered by solar flares that had occurred months earlier. These disturbances suggest that, even at such incredible distances, the Sun's activity can still send shockwaves echoing through the interstellar medium. The signals returned by these aging spacecraft are not mere scientific curiosities. They represent extraordinary endurance and engineering finesse. Voyager 1 and 2 now operate on extremely limited power, forcing mission engineers to make difficult choices about which instruments to keep running. Initially powered by 3 radioisotope thermoelectric generators, RTGs, their electrical output has been declining for decades. As a result, non-essential systems, including heaters, have been shut down, leaving some instruments exposed to freezing conditions they weren't built to withstand. And yet many of them continue to function well beyond expectations. This careful rationing of energy is a delicate balancing act, an ongoing effort by engineers to keep the mission alive for as long as possible. Among the most poetic elements of the Voyager mission is the Golden Record, a 12-inch, gold-plated copper disc mounted on each spacecraft. Conceived by a team led by astronomer Carl Sagan, the record contains greetings in 55 languages, a medley of global music, natural sounds, such as wind and birdsong, and 115 images showcasing Earth's cultures and ecosystems. Though the odds of an extraterrestrial encounter are vanishingly small, The record remains a symbolic time capsule, a cultural artifact drifting through the cosmos, possibly destined to outlive all other human achievements. The recent discovery that captivated scientists involved an unusual, persistent hum detected by Voyager 1, a low-frequency plasma wave. This faint background vibration reveals that the interstellar medium isn't as still as once assumed. It suggests a dynamic environment influenced by stellar winds, magnetic forces, and plasma movements, challenging traditional notions of interstellar space as a silent void. Every byte of data returned by the Voyager probes brings us closer to understanding our galaxy and informs the next generation of interstellar missions. But beyond the science, the Voyager story resonates on a deeply human level. These spacecraft were built in an era of rudimentary computing, nascent space communications, and short mission expectations. That they've survived nearly 5 decades is a testament to the spirit of exploration, innovation, and sheer persistence. Each signal Voyager sends is a whisper from a machine long removed from Earth, yet still tethered to us. Engineers and scientists who manage the mission often speak of the strong emotional connection they feel to these aging travelers. Machines that have become more than tools. They are cherished explorers,